Well, good afternoon, everybody. We will start to record the session, so please mute yourself and don't put anything in the chat that you don't want to be recorded as well. Welcome to the NOAA Environmental Satellite Enterprise Application and Opportunity short course, kind of a training session for students. And this short course is organized by the MS Satellite Meteorology, Oceanography, and Climatology SATMOC committee. And those short courses and the training sessions are designed as opportunity for our students during the summer to learn new and interesting satellite applications enabled by the research activities and new satellite products conducted by NOAA, other federal or university labs. It also provides an opportunity for those who are changing careers or moving to a position that requires increased environmental satellite knowledge with benefits from such courses. So my name is Jun Wang. I'm a professor in the College of Engineering, University of Iowa. I'm one of the MS SATMOC members. And besides me, there are also several other members that have done a lot of work on a bi-weekly basis, have meetings to put this session together. And I will put the link so that you can see their names in full in the chat. Today is our first session. Actually, supposed to be the second, but the first session was canceled because the leader person for that session was not feeling very well. So this will be actually first session that we planned for the summer. The session will be led by Professor Guilin Gao from Texas A&M University, and as well as her team members, which she can introduce later. And the session will focus on monitoring global lakes and reservoirs using multiple satellite observations. And Professor Gao has been in Texas A&M for a number of years. Her primary research are in hydrological modeling, land cover and land use change, water resource management, and soil renaissance in hydrology. And her work has focused on using multiple satellite observations like MODIS, spheres, Landsat, ICE-SAT-2 to monitor storage variations and evaporation losses over the global lakes and the reservoirs. Those are basically where we get our water, drinkable waters, right? in inland waters. Very important research work. And he also is a deputy chair for the AGU Hydraulic Remote Sensing Technology Committee, and is also a science team member for MODIS and the VIRS. With that, I will turn to my time to Professor Gao, and then you can take away from here.
Thank you very much, Professor Wang, for the introduction. Can you all hear me clearly?
Yes.
Okay. So good morning, good afternoon, and good evening, because this is an international open short course, and it's our great pleasure to be here with you the next couple of hours. So Dr. Wang has already introduced me, and I want to take the opportunity to introduce my PhD student, Deep Shah, who's going to work with me to give you this training session. So NOAA has played an important role in observing the Earth. So the very first NOAA weather satellite was launched in 1960. And during the last half century, NOAA continued working on this and observing the Earth. So it's an interagency and also international collaboration effort. So with all these satellite constellations, they really help us to better understand our planet from the atmosphere, ocean, and the land. Particularly, today we'd like to share some applications of using this low orbiting satellite to monitor the global lakes and the reservoirs. So when you have questions during the next 15 minutes or so, feel free to put in the chat and I will address them all together at the end. We plan to have a 5 minutes break, and the second hour will be led by Deep for which we are going to have some hands-on exercises so that you can really play with the data. In 1972, the crew of Apollo 17 took this very first iconic satellite image of the Earth, and they called the Earth the Blue Marble. So this is such a beautiful name, and it shows the uniqueness of our planet Earth is because of the water. And from space, we see water everywhere. However, if you look at the actual volume of the water we have, is much smaller compared to the Earth. So all of this water, if we condense them into a ball, this is what we get. A diameter is about 1/10 of the Earth's diameter. And the fresh liquid water is even smaller, and a big portion of this fresh water is locked in the ground in the forms of the groundwater or in the ice. So the fresh liquid surface water actually is only equivalent to a diameter of 36 miles. So we don't really have much water there. And of this surface water, the 87% of them are lakes and reservoirs. So these lakes and reservoirs are essential for us in many ways. So if you look at global lakes, there are millions of them there. And there are lots of smaller lakes in the higher latitude and some very large lakes like the Great Lakes. And then they play an important role in the hydrological cycle. And they are important for us human beings too, and vice versa. Human can influence the surface water both directly and indirectly. So to better understand the global surface water, satellite has been used a lot, especially recently. There have been a number of very wonderful global scale studies. And one paper published about a month ago by Yao, etc., they studied about 2,000 large global lakes and found over half of them have shown decreasing storage. And here I'm showing an animation of a few very famous large lakes that you can see the change, the declining of the lake storage can be caused by many things: climate change and human water uses, and all these will affect our life. In particular, there's one category of lakes is natural lakes. It's the man-made lakes, the reservoirs. So since the 1940s, reservoirs has becoming like more and more popularly used for managing the water on the Earth. In fact, the total impoundment is equivalent to over 30 millimeter sea level rise. So this is the most significant human intervention of our water resources. There are many benefits of having the reservoirs, hydropower generation, irrigation water supply, flood control, and recreation. So these reservoirs, unlike the natural lakes, because they are man-made, so you can see their distribution is very different. First, the United States has gone through in the 20th century the construction of the reservoirs, but then it slows down, and you can see the yellow colors shows the new constructions, the new reservoirs, which happens a lot in Asia, and also and there's a lot reservoirs in the global south, like South America and Africa. So these reservoirs can be affected by humans, and an example is the largest reservoir in the US, Lake Mead. And this stunning image shows you, on one hand, if you look to the right, the Lake Mead area has been shrinking due to lack of inflows and intensive water use. To your right, to your left, you can see as Lake Mead shrinks, the city of Las Vegas grows really fast over the last several decades. Another important factor for the reservoir water balance or the lake water balance is the evaporation. This has become a global phenomenon that since the 1970s, that the evaporation loss from the reservoirs has exceeded the combined consumption from the industry and domestic uses. And take Lake Mead as an example again, that its annual evaporation loss is larger than the Las Vegas Valley's annual water use. This is especially dramatic in arid and semi-arid regions. To measure the evaporation losses is not very easy. And traditional method is the pan evaporation, and which has a large uncertainty. Basically, you have this fixed sized evaporation pan and try to mimic the large lakes and reservoirs. And the more accurate one is eddy covariance, but it's fairly expensive and the data is very difficult to process. Eddy covariance data is typically used for research purposes. Another approach is called the Bohr ratio energy balance. It's relatively easier than the eddy covariance, but still we have very limited in situ lake evaporation observations. So why we use satellite remote sensing? First of all, the lake storage observations are very limited. And if you recall that there are millions of lakes globally, most of them, the vast majority of them, we don't have such observations. When we talk about reservoirs, one argument is that pretty much all the reservoirs are monitored. True. But other people monitor the data does not necessarily mean that they share the data, right? So especially if you look at the globe, nearly 50% of the global land is covered by international river basins. And again, the in situ reservoir evaporation is extremely limited to such data. Even in the US, we talk about like the eddy covariance data. Like in the US, we probably have less than 10 locations with like couple years. If you have couple years data, that's a lot of data. On the other hand, there's decades of the satellite observations that offer us a great opportunity. And next, I want to talk about the history of remote sensing of lakes and reservoirs. This all started with measuring water elevation. So until about a couple decades ago, like when people say remote sensing of lakes and reservoirs, they particularly by default, they are talking about measuring the elevation. But in fact, these were not originally targeted for these inland water bodies. The first efforts were, it was nice discovery that there was this ocean altimetry satellites measuring the ocean's elevation. The whole idea is that you send the radar signals and then the signal bounce back, you measure the time, then you know the distance. We call it range. Of course, there are a lot of processes in between. So when we take these measurements, these are pretty much like sporadic footprints globally. Then researchers found that we can use this to measure the elevation changes over large water bodies, like large lakes and reservoirs. So this chart shows the general timeline for the series of satellite radar altimeters since the 1980s. And you can see there are about over 10 missions out there, and overall they can generate pretty long records. In fact, there are 3 very well-known, databases or websites. We provide the link here. In general, globally, there are several hundred of large lakes and reservoirs can be measured. Their elevation can be measured using such approach. And because all these, if you look further, you'll see that these missions are from different countries, and they have different repeat period, and they use different microwave frequencies. So there's some discontinuity there. So I'm showing one of these websites is called the Global Reservoirs and Lake Monitor GREALM. This is one of the very popular website that where if you look at these hundreds of locations, you should be able to easily pull out the elevations. Here I show one example. This is the Lake Powell, and so the measurements we have are collected from multiple satellites, and you can see they have different frequencies, and there are certain periods that there's no data at all. Why? Because they all have different ground tracks. When we see that their repeat time being different, that means their ground tracks are different as well. So even we have hundreds of them, the data is not necessarily continuous from 1990 all the way to present. And the data quality varies too, because your adjacent topography of these lakes or reservoirs, the footprint size, or like you have lower quality when you go to the high latitude. So that comes to the question is that, what if we want more? What if we want more than just the elevation? What if we want more than just like limited amount of time coverage? So particularly for lakes and reservoirs, we want to know the storage. So how can we go like get the elevation or the area and the storage? Here's the good news. If you look at each water body, its elevation and surface area has a unique, relationship, like one-to-one type of relationship in general. For measuring the elevations, I just showed, there are different databases with the radar altimeter data loaded. And there's another type of sensor called LiDAR altimeter. And it's much smaller footprint so that you can capture much smaller water bodies. But there's always a trade-off between the spatial and temporal resolution. For instance, this satellite called ISAT-2, it has a repeat period of 91 days. But regardless, when we have overlapping elevation and area estimations, we should be able to establish such a relationship. And for area estimations, this is very straightforward. There are these optical sensors or like near infrared sensors that we can relatively easily extract the water extent. And we can certainly go use like active sensing like the star. So that's the basic idea. If we have this relationship, assume like a lake looks like a bucket, you have this relationship. If you can measure the elevation or the area, meaning that you can basically easily go from one to the other, assume for reservoir condition, if we have a reservoir, we usually know the reservoir's capacity, then we can estimate its storage. So in short, with area elevation relationship established and the parameters at capacity, we should be able to estimate the reservoir storage. For the lakes, we don't know the storage capacity, but we can estimate the storage variations. Let's look at the evaporation and the evaporation volume. First of all, the evaporation rate. As I mentioned earlier, it's very hard to collect the in situ data. Then we are thinking about how we can really get estimates of the evaporation rate at a large scale, pretty much at all these locations. How we can do that? The easiest way, not easiest way, is like the best thing we can leverage, we'd like to have to, is meteorology for things like those, like regular meteorology stations. They can collect the measurement of wind speed, you know, like relative humidity, temperature, this type of data. And but for lakes, there are something different. As I showed earlier, that when you have an evaporation pan, it's shallow, right? It does not represent the heat storage effect. And with the heat storage, the energy builds up in the water body. So there is a lag time. Even your temperature, air temperature, typically peaks in July or August, but the evaporation rate and the water temperature peaks usually 1 to 2 months later for the deeper lakes or reservoirs. And the other effect is the wind fetch function. The wind fetch, like when you have the wind going over the surface, it actually grabs moisture. So we have developed algorithm based on the Pellman's equation. I don't want to get into the details. Another thing I want to say is that unlike the storage part, this evaporation rate, there are many other different ways to estimate it as well. Today's training, we focus on this method we have been using. And on the other hand, evaporation volume, which is very important, right? Because we want to know actually how much water's lost, from these lakes, so that we can better manage the water. So for that, we just time the rate with the area. If we have ice over it, we assume the sublimation is very small. We can ignore that part. We only calculate the water part contributions. So here, get to the MODIS and WIRS. MODIS and WIRS are very well-known sensors. How well-known? Here's an example. What you are looking at is the very first image, one of the first images shown on the first iPhone when iPhone 1 was released. So over the years, MODIS and WIRS has been used for observing land, ocean, and atmosphere. And it has brought a lot of economic values. There are lots of products from like monitoring the air quality to, to the ocean algal, algal blooms and fire and pretty much everything environmental related. And so another thing with the MODIS and WIRS is that WIRS is by NOAA. It essentially for continuing the MODIS. MODIS on the satellites like Terra and Aqua, and then after this, Terra and Aqua still functioning till today. And then WIRS will take over, and the following satellites carrying the WIRS sensor are scheduled all the way to the 10 years from now on. So these will create a very long, valuable records. So now we want to talk about the global water reservoir product. So with this, why we want to use the MODIS and WIRS for this purpose? First of all, as I mentioned earlier, that we can estimate the storage if we know the area. Why we care about this area? The nice thing about the area observations is that all these sensors are imaging sensors. they don't pick. They don't, in general, they don't say, okay, I don't have an overpass over a certain water body. And there have been lots of studies showing that just using the surface reflectance data, we should be able to extract the area, and therefore we can infer the elevation storage. And then the reservoir evaporation, we talk about heat storage, and that can be estimated by leveraging the land surface temperature measured over the water bodies. And with this together, reflectance and LST, and driven by the meteorology forcings, we will be able to simultaneously estimate both the storage and the evaporation. And this is very, very important, because this way we are capturing multiple water body terms of a water body. Most of other, satellite-based, products or whatever, they focus on one or the other. But with this global reservoir, water reservoir products, we are trying to present, deliver a standard product. Basically, we call it everything everywhere all at once. So it's one stop for you to choose. And then what this product is like. This product covers 164 reservoirs, and this represents nearly 50% of the global capacity. Why there's only 164? This is because we use the radar or LiDAR altimetry data to combine with the area to develop the area elevation relationship. We said that's very important. A few years ago, we were only able to pick about over 300 locations with reliable qualities. And I don't know who's drawing. And then because of that, we decide we want to focus on the best locations. That's the spatial coverage. And in terms of the product variables, we have two temporal resolutions. One is 8-day, the other one is monthly. For the 8-day, we have the area elevation storage. This and for the monthly, we also added the evaporation rate and volume. The MODIS-based product is currently, available, has been released since 2 years ago, and its counterpart, Weir's product, will be released later this year. And just very briefly, how this algorithm work is that for 8-day, we use the MODIS. We use MODIS as example. We use the reflectance, and then we conduct area classifications. Then we count up the pixels classified as water, and then we put this area as an input for this AE relationship, which is pre-established. And then we can estimate elevation storage. For the monthly, for the storage and elevation part is very similar to the 8-day, but monthly we focus on using the LST data and meteorology data to calculate the evaporation rate using the Paman's equation. And then we type the area, get the volume. So this is how roughly works. We have publications if you want to dig into the technical details. So here just one example, because earlier I said, like with these satellite images, we can cover pretty much every locations, but there's a big factor is that like cloud contamination. So how we deal with this, we develop algorithm such that we can, do the first round of classification. For example, this is the raw reflectance data. And if we take out the cloud covered area, then we have this partial data coverage over reservoir. And then for whatever we have, we can classify. And then we have these water pixels. Of course, you know that within a reservoir, the water should be all connected. Then how do we know that this no data, like cloud covered pixel, should be defined as water or land? So we developed this algorithm. Essentially, it relies on the water percentile images, right? You know, when you have a lake, there are shallower parts, there are deeper parts. Deeper parts, if you know, even I cover this big portion of the lake, if you see this part being, water, then you know the similar depth area should be water. So that's the idea. With that image enhancement procedure, we will be able to generate, the full area estimation. So again, I don't want to spend too much time on this. Once we have area, we can infer the elevation and we can calculate the storage. And the nice thing about this is that we have the data set started from 2000 and until like a couple of months, prior to present. And all these locations have exactly the same data record. So another thing is that whenever we have a remote sensing product, we want to validate them. This is just to give you like some idea. We look for in situ data, and that said, with this very broad, global audience here, if you ever have in situ data, we are and willing to share, that's always much appreciated. So the reason is that when we validate this, then we will have better confidence and understand the accuracy and uncertainties, and then we can, apply this to globally more locations. And I will be very brief on the validation, but just keep in mind this is a very common exercise. For the evaporation part, here shows this complex evaporation process, and we developed an algorithm called lake temperature evaporation model, which is used for this global reservoir product. So we incorporate this surface area estimation, and not only the area value, but also, we see these two-dimensional changes of the area, so that we know that there's fetch length depends on which direction the wind blows, and then we can adjust this and make this difference between the saturated vapor pressure and the actual vapor pressure, more accurate. That's the wind function part. And then for the heat storage, we use the satellite to measure the water surface temperature to constrain our algorithm so that we can estimate the vertical temperature profile. So here, just briefly showing that we collected, we collected the data. Other people conducted this in situ experiments using eddy covariance instruments. We, got those data and then we use them to validate our evaporation algorithm. Here, I want to point out, you see, this red is with the heat storage considered. The blue is without heat storage considered. For Lake Taihu is a lake in China, is fairly shallow, so there's not much different. But for deeper lakes like Lake Mead, you can see that without including the heat storage, you get a large amount of error as compared to the observations. So this slide just give you some idea what we can offer from this product. Like with each location, we have actually 5 variables when at the monthly time step. And this product is publicly available. In fact, that will be one of the focuses in the second part of today's training session, where we are going to show you how to access this data. And there are also some interactive websites like this one. You do not need to have sophisticated like skills whatever. You just go there, find the reservoir of interest, and you can make plot and extract the data. And so far, like the last few slides, we have been talking about MODIS. We said that the VIRS product will be released later this year. And one important part is to evaluate the continuity between MODIS and VIRS product. Here just shows an example. And the motivation is that we have MODIS from 2000 till present, and VIRS started collecting data over 10 years ago. And then VIRS is a sensor that will continue in the next few decades. So what are we going to do is that when we want to study things related to climate, we want to make sure these measurements are consistent first. So that's another aspect we have been working on. And earlier I mentioned that we only had, only have 164 locations for this standard product, but over time, there was more available data, especially with the launch of the ISAT-2, which has this laser altimeter, which was launched in 2018, 5 years ago. We get more elevation data for smaller water bodies. So our group currently working on extending this to over 2,000 locations, and also not to limit us to reservoirs, but also open up for the natural lakes. So this will cover a good portion of the global land surface, and we are going to continue working on this, the suite of variables for this data set. So now I want to talk about some other studies using the Landsat. Although, Landsat is not a NOAA satellite, but it's like commonly used by many people, and primarily because it's high spatial resolutions. The first Landsat satellite was launched about 50 years ago, and similarly, there's this long-term plan for using it to observe the land surface, right? But according to the name, this is a land satellite. So I want to show a couple of data sets. The first one is the lake evaporation data set. With this, we use the global lake database, which shows where are the locations of these lakes and what's their shapefile. So we are able to estimate the evaporative water loss for each of these 1.4 million global lakes at a monthly time step from 1985 to 2018. And we provide not only the rate, but also the area and the evaporation volume. So all these together, give us some idea how the lake evaporation been changing over time. What we found is that if you look at this figure here, in the most of the thermal regions that the evaporation volume has been increasing. Some of them were caused by the increasing of temperature. Some are caused by the increase of the surface area of the lakes, and some of them is caused by the decreasing of the ice period or ice cover. So this is clearly very related to the climate change. And also in this study, we compare the lakes and reservoirs. We found out very interestingly that the evaporative losses over the reservoirs are much faster than the increase is much larger than the natural lakes. So this data set is publicly available. And again, in the next part, Deep will show you the use of this website, and will give our participant ample time for you to play with it. And another one is the estimation of global reservoir storage. And this is a paper actually we just published last week. We put a lot of good effort into it and got some very interesting findings. You know that if you look at the accumulated storage capacity over the last 20 years, new reservoirs continually being built, and mostly in like Asia, but also quite a lot in South America and Africa. And it's very clear that we know the global storage is being increasing, but we want to compare the new reservoirs with the existing reservoirs like constructed before the 21st century. So we come up with a term called normalized storage. Essentially is that you have an actual storage and you also have a storage capacity. If we take the ratio, it's the relative percentage fullness. This way, we can look at a region. This region can be a continent or can be a basin. So I can lump up all this storage and all the storage capacity and see the overall performance. So in this figure here, we lumped those pre-2000 reservoirs and the post-2000 reservoirs. We look at their normalized storage. We see that the newer reservoirs, the percentage fullness is much lower than the earlier constructed reservoirs, and they also have larger, variations within a year. So that's something quite interesting we found. And similarly, this one has like over 7,000 reservoirs, and we provided time series for each of those. And when we look at by continents, we compare the storage, which is in blue, with the normalized storage. Globally, you can see this X shape is like they go against each other, right? Even you have growing storage, but this normalized storage decreasing. And this contrast we see most in where we see in Asia, like where the most new constructions are found. Even the normalized storage change, it decreases, even though in Asia it's not significant. Then the other places are Africa and South America. In North America and Europe and Oceania, we don't see much difference. And here, similarly, for each location, we are able to, to show you in the next exercise, you will be able to, select a reservoir of your interest and display the data and pull out and discuss, what's happening. So, as we said, that our capability for observing the Earth continues to grow, and this is very exciting. and one new satellite. As I told you earlier, like with our remote sensing of lakes and reservoirs started with ocean observations, right? And then I mentioned a few times this satellite called ISAT is primarily for measuring, ice-covered glaciers, the height of top of the clouds. It's not intended for land, even it has land applications. So last December, finally, this surface water and ocean topography satellite mission was launched, and it is really, it really brings us to a new era. Even we are all patiently waiting for the new data to be released. This satellite uses the INSAR technology. What this means is that using this active radar technology, we can have observations day and night and under all weather conditions. And the measurements, as you can see, is no longer like footprint by footprint. These are images. So we are getting the images of the water elevation, and pretty much we can cover most of the water bodies as small as 250 meter by 250 meter. So that's really exciting. Oh, sorry. Okay, so next I want to talk about some applications so that to give you some idea when we have such data, what we do with it, right? So one application is to look at drought. As you know, that drought can be classified as meteorological drought, which typically use precipitation as an index. And then there's agriculture drought, and oftentimes we use the soil moisture to represent. And then there's a hydrological drought. This could be, based on runoff, stream flow, groundwater, or we can use the reservoir storage or evaporation as an indicator. So in fact, if you look at all these droughts, they cascade, meaning that, the drought event triggered by short of precipitation, then it affects the soil moisture, then it affects the stream flows, and certainly it affects the reservoirs. And whenever we have a drought, we talk about, the reservoir is almost empty, right? That's what we hear a lot the last few years, for instance, Lake Mead and many locations. So here, example, like we can look at the storage. Some drought can last very long. For instance, Lake Mead, partly is due to the weather and climate, and also this reservoir-based drought can be affected by human as well. Like if you continue, pumping the water, then that will reduce the storage. And then the other example is, this reservoir drought in Australia, where we have extended like 5-year-long drought, but the reservoir recovered. So another idea we want to share with you is the using how we can use this remotely sensed reservoir information to improve water management. Here, about a year ago, my group in collaboration with DRI and Virginia Tech and got a NASA project with the end user as the Bureau of Reclamation, who's in charge of the reservoirs of the entire Western US. So we are doing a reservoir evaporation monitor and also forecasting. We use different satellite data to help us to estimate the reservoir surface area and also fill in locations when there's no in situ storage or elevation measurements. So we are also extensively working with stakeholders and see how we can help them to use this information. In fact, this project earlier phase was like with the Texas, we already developed evaporation monitor for the state of Texas, over 188 reservoirs. So the last few slides, the whole idea is that to throw out something like, so that in the next hour when you are in the hands-on session, what you can look for, like what are the things that you are interested in. So with that, I stop here. I see the chat. Seems like there are a few questions there, and I will address those first, and then after addressing the questions, we'll take a 5 minutes break, and then we are going to move on to the second part, the hands-on exercises. And I mentioned a number of publications which are all listed at the very end of the slides. So now I think I can, let me see. There are some questions here. Let me see. Yeah, please, feel free to put your question in the chat, or if you feel unmuted and asking the question, that would be good too. Let me see. Yeah, I see. Yeah, some greetings from Vietnam. And why the reservoir evaporation loss increase faster than natural lakes? Okay, this is by Ali. That's a great question. We thought about that too. Why the reservoir evaporation loss increase faster than natural lakes? My thought is, first of all, if you go back, picture, the global lakes and the database, and also the global reservoir database, right? And a lot of the reservoirs are constructed in these arid and semi-arid regions, primarily for, a big function is for water supply. And also reservoirs, so when you have the reservoirs depths, in general, they are shallower on average than the natural lakes. And then because of this, their heat storage effect is relatively smaller than the natural lakes. So they are kind of saying like they are more sensitive to these all these changes. So that's my interpretation. It's like if you have, the same temperature increment over the, reservoirs, which is relatively shallower, in more placed in the drier locations, but like lakes are like a lot of times more on the, not so dry conditions. Then they tend to have faster increase of the evaporation loss. Thank you. Yeah. Okay. We got the next question from Michael. I have a question about the SWAT satellite. Why is it going to observe small rivers below 100 meters in width, but lakes only as big as 250 by 250 meters? Okay, again, that's a great question. I would say, first of all, there is this science requirement or application requirement. So when the SWAT satellite mission was designed, as you brought up, I didn't get to that detail, is that a big part is to use SWAT to measure the water elevation, particularly in the rivers, such that we can estimate the river discharge. And we have very few river discharge data globally, especially in those developing countries. So if you look at like about few years ago, there are, you probably have seen this, there's this type of showing like on one hand, on one hand, they show the dimension. The other hand, they show what's the percentage of, covered, right? So my take on this is that if you can measure the lakes 250 meter by 250 meter, you have got like more than like 90 or 95. I'm throwing out a number here. That's the idea, is that we can capture the majority of the lakes. But if we do the rivers, we need to have a higher standard. So because if you want to, like, your goal is to go, say, I cover 90% of the rivers, you have to have a much smaller one. That's my take on that. I'm not so sure whether that is true or not. I mean, like, I'm not so sure, but basically with these two different criteria, the science goal in terms of how much we can cover relatively should be similar. That's my take. Yeah, and then there's also for the lakes, they have these measurements. They are going to average them up over the lake. I think that's another exercise. Beyond that, I'm sorry, I don't know too much. Hopefully that answers your question. And yeah, Augusto has a question. I understand the usefulness of satellite-based reservoir monitoring in poorly monitored regions or locations where countries don't share data, but what's the real contribution of doing it in US reservoirs? Reservoir data such as level storage, basic, let's see, information stakeholders already have operate reservoirs. Also, that data is already open available. Wouldn't the application of such an approach be more useful elsewhere? That's true, Augusto. I would take this from two perspectives. Earlier, I mentioned that for any satellite product, it is critical for us to, validate the results. Over the US, because we have so many, observations, that we are able to, evaluate the performance of the product. This is from a global point of view. If I'm doing a global reservoir product, the reason I include US, to benefit the users more is more like indirectly. I do the validation to test the algorithm. Within the US, true that the data, a lot of data is shared, but you would be surprised. There are also lots of data not shared or even collected. For instance, I mentioned this Western US project that in the Upper Colorado, there are locations that they have data, but they are not really processed or shared. In fact, like, we have been working with them, like trying to contact and to find out the data, and they probably collect certain period and they are not really coordinated. So even within the US, for the smaller reservoirs, there are still benefits of using satellite data to help us to fill in the observation data gaps, because the observation data may not be continuously, may not be include a very long record over certain locations. And there's other aspect is the evaporation. With the evaporation, basically, when it comes to evaporation, even the US is much handicapped. So if we incorporate the land surface water temperature measurement, that will be, that will help us better at this estimate the heat storage and such. And let me see, there are a few more questions. I will try to be brief. And how about this? We take 5 minutes. For those of you need, you can 5 minutes later we'll start the second session, and I will continue addressing the next questions. Is considering heat storage in the Pemman-Matisse equation important given the time scale you are working at? That's a very good question. That's why we continue pushing, from the monthly to daily. For the monthly, yes, it still is important for the large and deeper lakes. As I showed the validation, like if you look at relatively shallower lakes, I'm saying, like, for instance, if in a lake which is 5 meters or less deep, that heat storage effect is not that significant at a timely scale. That's why we want to push it to, hopefully with this NASA product in the future, we can push it to 8 days. And with the Western US product, we are working on daily. In short, that's a great question. Thank you. And when is going to start? Yes, in 5 minutes, 1:05. Presentation. My question might be the possible reason of having diminishing storage in the recent years compared to the earlier period. That's a good question. I will be brief. You can read our paper, which we discussed. For the Global South, a lot to this is, like, if you look at the recent years, there's a decline of runoff there. That's, in general, is for this part, it's like for old reservoir, new reservoir, all combined. In the Global South, we see a decreased runoff in recently. And then there within a basin scale, that's what we found, like the new constructions tend to have a smaller one. I would guess, like, with new reservoirs, how it's managed, and also it's like you only have this much. Like when you have more added, your per share could be a bit less. Those are my two things. I'm happy to, feel free to email me to discuss more. And then, okay. Think there's also, to my understanding, altimeter observation. We go over all the reservoir. How did you develop area for other lakes? Yes, I mentioned, probably I didn't say it very clearly. The reason we are able to, there are two things. The first one, for us to plan to extend this record to over 2,000 locations for multi-some years, we have been using the ISAT-2, which has sparse measurement every 3 months, but has very high accuracy and captures smaller water bodies, so that we have fewer observations, but pretty accurate. We can develop actually better area elevation relationships than with the radar. So that's why we can do those. And for that global storage declining paper, we use the combination of this, altimeter calculated AVE relationship. And another one is the type we assume reservoirs comes, like there are, like, say, about a dozen different standard shapes. and then you try out each one and find the one that's best performing, give you the most reliable storage at capacity given the area estimations. There are a lot of more details if you read the method section of that paper. Okay, with that said, I think I'm on time, and I know many of you are very excited to get your hands on this. So I'm going to give the floor to, I think I missed, okay, there, okay. Yeah, I will give the floor to Deep. Yeah, Deep, go ahead.
Thanks, Dr. Gao. Can you see my screen?
Yes.
Okay, so hi everyone. My name is Deep. I'm currently pursuing my PhD under Dr. Yulin Gao at Texas A&M University. My research interest lies in monitoring global lakes and reservoirs, especially in the data scarce region, or reservoirs located in international water basins. Also, my research focuses on droughts in reservoirs and lakes and how human influence these droughts and reservoirs. So for the part one, Dr. Gao mainly explained about the algorithms and how remote sensing can be utilized to monitor global lakes and reservoirs. And in this part, we are focusing on the data sets that we already developed. So you don't need to perform any analysis, or you don't need to play with the algorithms. You already have we already did for that for you all, and these are the data sets that we developed. So before we start exercise, the hands-on exercises, let me introduce our team who will help you during the exercise, hands-on exercises. So we have Anshul, Tuhidur, and Shrai with me, who will be your point of contact during the exercises. So basically, we have 3 exercises, and for all three exercises, all the participants will be divided into 4 breakout rooms, and in each breakout room, you will have one person from our group who will assist you during the exercise. So for breakout room 1, I will be your point of contact. For breakout room 2, Anshul will be your point of contact, and for breakout room 3 and 4, Tuhidur and Shrai will be your point of contact. Don't worry if you don't remember their names; they will introduce themselves during the when you're moved to the breakout rooms. So as Dr. Gao mentioned about the different data sets, we are here focusing on 3 global data sets that we developed. The first one is Moody's Global Water Reservoir Product. The second is Global Lake Evaporation Volume data set. And the third one is Global Reservoir Storage data set. So I'll briefly talk about each data set, and I'll show you the website that we developed to visualize the data, and then we will have exercise for each of the data set, like how you can use the data set, and there will be some questions that you need to answer for the exercise. So the first one is about the Moody's Global Water Reservoir Product. To briefly give an overview about the product, it contains data for the 164 global reservoirs, which approximately covers 46% of the global capacity, and it is available at 2 different temporal resolution. One is at 8-day, and the second is at monthly. So the 8-day product is known as the C2 product, and the monthly product is known as the C3 product. Now the first question arises about how to access, extract, or visualize this data. So we have developed the user guide for this product, and this is the user guide. Can you guys see the user guides that I'm sharing?
Yes.
Yes. So this is the user guide. In this user guide, we are we explained about the algorithms that are used to develop the data product, then about the naming convention, data layers, metadata, and example codes for each product. One is for 8-day and the other one is for the monthly. Yeah, my screen got blank, so I couldn't see that. Okay, so the user guide contains, as I said about this algorithms, the naming convention, like once you download the file, what will be the different information in the file name and how will you interpret that. Then something about the data layer. So like once you download the file, there will be like data layer called lakes, and when you open the lakes, it will have the lake ID, its location, which is the longitude and latitude, and lake area, elevation, and storage value for that particular day. This is for the 8-day, so we have three variables available at 8-day: temporal resolution, area, elevation, and storage. Then something about the units of the each variable. Similarly, I will be very brief about this. You can look into the user guide, look at the user guide later on, and Anshu will provide the link in the chat, so you can always recheck that. Then about the monthly data, we have the two more columns about the lake evaporation rate and evaporation volume corresponding to that lake ID. Now the question is, what does this lake ID mean? Like, what is the reservoir corresponding to this lake ID? So to that, to answer that question, we have like a detailed table available which shows the lake ID and corresponding reservoir name and the different attributes of that particular reservoir. So this is very important table which gives you the overall idea of the product and what different reservoirs we are covering in this product and their capacity values. We also have some codes available written in MATLAB and Python. So if you are not familiar with the programming, you can just copy this code and copy and paste this codes to MATLAB or Python and just extract the data using this already developed codes. We also have one code which is for outlier removal and gap filling, which is known as outlier removal and gap filling script. So during when you download data, you might find that there will be some outliers in the data. So you can remove the outliers and fill the data gaps using linear interpolation by using this script. Again, you don't need to go into the details. You just need to copy and paste the script and it will work. So coming back to our data set visualization. So NASA has developed this amazing website where you can visualize the data that we generated. So here are the 164 locations that are covered in the product. What you need to do is just zoom into the reservoir of your interest. So for example, if my reservoir of interest is this, then I just need to click on the reservoir. Now it will show the name of the reservoir and under the selected sites column. Then you need to select the data set, which will pop up the different options available. So you need to select the Terra plus Aqua, whatever the options are available right now. Then you will have the two different options available for the two different products. So C2 is corresponding to the 8-day product and C3 corresponding to the monthly product. So so as of now, let's select C3. Then as it's a monthly product, you can have different variables to select like what you want to actually visualize. So for example, if we select reservoir storage, and then you need to just add to the plot and just click plot. So it will create a nice storage time series from 2000 to the present last available data that is available. And there are different options you can options available here. For example, if you want to download the plot, you can download plot as .png file. If you want to edit something in this plot, you can use the chart studio, and for that you need to make an account, but you can do it. Then zoom in, zoom out, auto scale, and if you want to see the particular value in that particular day, that also you can see by just moving your cursor. You can also just select the data period that you want. For example, if I just want to select the data after 2015, then we just need to drag this button from left to right and just select the data period that you are interested in. So here we selected from 2015 to 2023. You also can download the raw data by clicking on the statistics link. Once you click on the link, you can download the raw data that are used to plot this time series. So when you open the data file, it will have all the 5 variables like reservoir, storage, area, elevation, evaporation rate, and evaporation volume for that particular location. And here you can see the file. So this is how it will look like after downloading the raw data. You can also select the location by name. For example, I know that Lake Mead is already included in the product, and you can use the user guide to see which lakes are actually, which reservoirs are actually included. So you can just type a name here, and you can also add reservoirs by the name. The other thing you can do is like you can plot different variables together for the same reservoirs. For example, like select Lake Mead, and here we already selected the reservoir storage. Let's select some other variable also. Like for example, we are interested in evaporation rate. We can add the evaporation rate. We can also add other variables such as reservoir area, and then just plot. So it will show all the 3 time series for all 3 variables. And here in the top, you can find that plot 1 stands for the storage, plot 2 is for the evaporation rate, and plot 3 is for the reservoir area for this location. And if you want to just see evaporation, for example, if you want to just see evaporation rate, you can click on the other variables time series, and it will be just disabled. So here I'm just showing like let's disable. So I disabled the plot 3. So here it's showing just plot 1 and 2, and here you can simultaneously see the both data values in blue and orange. What is the corresponding data values in storage and reservoirs for that particular day or month based on the product that you selected. You can also select multiple locations. For example, let's select some other locations to give you an idea. So for example, in India, you can select maximum 20 location for visualization. So for example, here I have selected 6 location, and for this 6 location, I want to see the evaporation volume, for example. So you just need to select evaporation volume and then add to plot. You can directly take the average of this all 5 sites evaporation volume by clicking on this average among sites, or you can do it after plotting also. So here it shows the evaporation volume time series for all the 5 locations, and you can see the name here. For plot 1, it's for this location. Plot 2 is for this location. You can turn on, turn off different time series, and for like if your focus is on some particular reservoir, you can just keep that on, and you can turn off all rest of the reservoir time series. You can also show average time series. For example, I'm just interested in showing using the average. So here is the average time series. You can also show the standard deviation. So we selected 6 sites. So based on that, it will also show standard deviation. You can also take the temporal average. So currently it's for the monthly product. So you can make it a yearly also. You can make it 16-day also. All this you can do and save your figure as a .png file. And for downloading data for individual reservoirs, you can click on that link for that particular reservoir, and it will get downloaded. So this was all about this data product. More you can do by yourself during the exercise and explore different options available. So yeah, let me go through the exercise section clearly so everyone will be on the same page. So firstly, we will divide all participants into 4 breakout rooms. And as I mentioned, there will be one person from our group to answer your questions or assist you during the exercise. You need to go to the same website that I explained and select the reservoirs in your country or area or whatever you feel you are interested in, and explore like what's happening in these reservoirs in different variables that we offer, like for example, area, elevation, storage, or evaporation losses. You can see, you can find that whether it's declining, increasing, or there is not much change in that reservoirs, and what might be the possible reasons. I know we are not expecting to know you the real answer, but you can just Google it or ask the Chat GPT or look it in your way to find out the reasons, like what might be the reason behind this variation that you observe. Then after so this exercise is for the 15 minutes. After few minutes, 7 or 8 minutes, the group like the group leader who will be in your breakout room will send the link for the Google Slides, where you can upload a picture of time series of variables that you selected for 1 or 2 reservoirs, and you can mention just write a short comment about what you observe in this figure and what might be the reason that you found out. And as I said, you don't need to be correct. This is just a fun exercise, just to get to familiarize with the data set that we developed and what different application that you can use in. So just thinking on the from the reservoirs perspective, nothing else. So don't worry about like what might be the exact answer or reasons for that. It's just a fun exercise, as I said. So Dr. Gao will help us divide us into the 4 breakout rooms, and you will see the small pop-up window coming to your main screen to asking for you to join to that breakout room. This will be like random, so just click on the join breakout room, and then the group leaders will help you to go ahead from that point.
Yes. Thanks, Steve. So I'm going to open all the rooms, and I said all these rooms will end in 15 minutes with 60 seconds advanced countdown. Yeah. See you there.
Thank you.
So also, Dr. Gao, one thing I want to mention is I will stop recording here because cloud recording is not able to record every breakout room. Okay.
Okay. Yeah, that's fine. Yeah. Let's see. I think I need to do this breakout room.